Good afternoon, ladies and gentlemen. Thank you very much indeed for coming. It is an honor for me today to present in front of you to deliver my team paper presentation. My name is Ina Dulasmana, and the topic of my presentation is solving container storage problem using particle swarm optimization algorithm with multiple social learning structure. First, I will explain about the background of our research. Sea transportation is one of the important components in international trade. In 2017, United Nations Conference on Trade and Development records the total of international trade commodities transported by sea reached 10.7 billion tons and experienced growth of 4% from the previous year. This happened mainly after the introduction of containerization in 1956. The effect also greatly impacted Indonesia as a maritime country and result in the increase of container throughput from 2014 to 2018. Container terminal is an area for carrying out loading and unloading activities of a container ship. It has an important role in improving the transportation value chain to move the containers globally. Every day, container terminal face several complex problems to schedule all operational activities simultaneously. They should always continue to improve its performance as the container demand is significantly increased from time to time. Storage problem is one of the optimization problems at the operational level in container terminal to be solved. The objective of the storage plan is to minimize the number of shuttle moves during the route of ship while considering several factors, namely size, type, weight, destination of containers, as well as the ship stability. This problem falls into the NP-hard category and later can be formulated as Container Stowage Problem, or CSP. Other factors should be considered before solving container storage problem is the size of container, and then the type of the container, then the weight of the container, the destination of the container, since a group of containers could have 2 to 3 different destinations, and the last is the ship stability. Although many studies have been offered for container storage problem implementation, only few applications are available for covering 5 important factors in storage planning. The first research is done by Ambrosino on 2010 using N-colon optimization metaheuristic. And then the second has been Putamawa and Santosa on 2016 using the B-swarm optimization. And the last is Matsaini and Santosa on 2017 using particle swarm optimization. In this study, we designed a metaheuristic approach using GLN-PSO to solve container storage problem, considering the factors mentioned above. The GLN-PSO algorithm is a development of the PSO algorithm that has been used in previous studies and is proven to outperform the prior algorithm. And GLN-PSO has been demonstrated to be an efficient algorithm. And then next, I will explain about the problem definition and mathematical model. To identify the unique location on the ship, the containers use a naming system with a standard index. The index used to describe the location of the containers are namely bay, row, and tier. In particular, each location is addressed by the following identifiers. First is bay. It is counted from the bow to the stern. And then the second is row. It's counted from the center to the outside. And then tire, it is counted from the bottom to the top of the ship. The basic container storage problem model used as a reference in this study is the model previously used by Ambrosino. This model considered the factor of size, type, weight, destination, and the stability of the ship. The container storage problem mathematical model consists of a single objective, one decision variables, and 18 set of constraints. And AMPL software is used to solve the mathematical model for container storage problem. However, when the numbers of variables and constraints in this model increase as the size of the problem enlarges, AMPL might fail to solve the problem to optimal solution. Therefore, the GLN-PSO algorithm is proposed for solving the GSP, and this algorithm finds a near optimal solution in a reasonable computing time. The objective function is to minimize the total loading time, and then the first three constraint explain how a location in ship can only be occupied by one container only. And then the second three constraint explain the concern with capacity limit from total ship capacity, maximum weight in stack for 20 feet, and maximum weight in stack for 40 feet container. We also have the constraint that guarantee the ship stability for like left-right stability and anterior-posterior stability. And then the 20 feet container and 40 feet container cannot be stacked in the same place. And then the next constraint guarantee that containers with earlier destination should be placed on top the next destination container. And then the next constraint deal with the 20 feet and 40 feet container arrangement in a bay and tier. Also, heavier containers should not be placed on top of a lighter container. Lastly, the decision variable for this problem is the variable will have a value of 1 if container C occupies location L and 0 if not. To apply the GLN-PSO to the problem, we must clearly define the solution representation and decoding method. Thus, the next subsection will explain the proposed algorithm. To apply the GLN-PSO to the problem, we must clearly define the solution representation and decoding method. The type of representation solution used in this study is continuous, which will be later converted into a discrete form. The representation solution will show the location where containers are placed on the ship. Therefore, the representation solution will be in accordance with the number of containers to be arranged. Each container will only occupy one location on the ship. And then the solution representation is built as follows. Each location on the ship is a label with a name. For example, a ship with 3 bays, 3 rows, and 3 tiers will have 27 possible location. Using the GLN-PSO random search mechanism, the algorithm is used to solve small problems consisting of 5 containers with a ship that consists of 3 bays, 3 rows, and 3 tiers or 27 position. And here is the detail of the 5 containers used. Also in the table below, you can see the loading time detail for each row. Using the GLN-PSO random search mechanism, the algorithm is used to solve small problems consisting of 5 containers, and the result obtained as follows. And then a solution in continuous value is then decoded to turn it into a discrete value by rounding it up. The interpretation of the result of the GLN-PSO algorithm is as follows. The algorithm provides an objective value of 600 seconds and a penalty value equal to 0, with the detail of the bay, row, and tier indexes as follows. The container 1 is placed at the location 132. Container 2 is placed at a location 133. Container 3 is placed at location 131, and container 4 is placed at location 112, and container 5 is placed at location 211. To calculate the Gsp solution, this algorithm presents a procedure for calculating the objective function value. And then the selection of parameters in the PSO algorithm is the main key that affects the performance and the efficiency of the algorithm. The basic PSO algorithm is influenced by several parameters such as the number of particles, number of iteration, the inertia weight, and the velocity constraint. The parameter tuning is done on trial error basis with a tuning scenario based on research from you et al. And after a preliminary test, the best combination of the proposed GLN-PSO parameters used to solve the CSP test instance are the number of particles is 30, the number of iteration is 100, the inertia weight is 0.3, the velocity constant for individual, group, local, and neighbor is 0.9. And then the next section is result and discussion. The data used in this study consists of 2 types, namely small instances and medium instances. Small instances consist of 5 until 27 containers, and this data can still be solved using an exact mathematical method. Meanwhile, the medium instances consist of 100 until 140 containers, and this data can be solved using an exact mathematical method but requires a long computational time. These two types of data are used to see the characteristic of the GLN-PSO algorithm as the complexity of the problems enlarged. And then each for the small instance and medium instance consists of 20 instances. In both small instance and medium instance, the problem parameter collected included a container parameter, and then ship parameter, and a time parameter. There are 20 small instances that are solved using the GLN-PSO and PSO algorithm and the exact model in Ample. The results of the implementation can be seen in this table. The comparison between the PSO and exact model shows that the exact model still outperform the PSO algorithm by 0.8%. The comparison of GLN-PSO and the exact model also shows that the exact model is still superior by 0.07%. Meanwhile, the comparison between the PSO and GLN-PSO algorithm shows a difference of minus 0.72%, which means that the PSO algorithm has a value that is not better than the GLN-PSO algorithm by 0.72%. And for small problem size, the average value generated by both the PSO and GLN-PSO algorithm has not been able to outperform the exact model values, but the GLN-PSO algorithm is superior to the PSO algorithm. For medium instances, it is evident that the PSO and GLN-PSO algorithms can be used to find solution when the size of problem is enlarged. The gap that occurs between the GLN-PSO and PSO equivalent to 27%. For computational time, GLN-PSO also produce a slower time with 8.2 second difference or 36% compared to PSO. And this is the implication of a wider search for objective value. From this information, it can be concluded that for medium instances, the GLN-PSO algorithm has not been able to outperform the PSO algorithm, both from the best objective value and the computational time. And then for the conclusion and the future research, this paper has proposed GLN-PSO, which includes the consideration of 5 factors in solving container storage problem. And then the objective function is to minimize the number of shuffle movement by minimizing loading time of containers. For small problem, GLN-PSO is superior to the PSO algorithm in terms of objective value and computational time by 0.72% and 0.172 seconds. For medium-sized problem, GLN-PSO has not been able to outperform the PSO algorithm, both in objective values and computational time, and the gaps obtained are 27% and 8.2 seconds. The GLN-PSO is suitable for use if activity does not involve large number of containers because the algorithm has not been able to accommodate the additional complexity of the problem. Future research may focus on adding heuristic method to the GLN-PSO algorithm, improving neighborhood structure use, or changing the local subset. And then the algorithm will later can be used to be implemented in problem with more than 1,000 containers to solve the container storage problem for a larger ships. And then container storage problem model also can be developed to accommodate container types other than general dry container, such as a river, flat tray container, open top container, or etc. And then, ladies and gentlemen, this is the end of my presentation today, and thank you very much for the attention. Thank you.